Do you want to automate, streamline working with data, spreadsheets, and databases? Then let's dive into programming right here, right now. Hello everyone. I originally made this video for an overseas audience, but I noticed some interest from my English-speaking community, so I decided to quickly translate it. I also increased the speed a little, so if it feels too fast, you can slow it down in the settings. Today, our task is to create a test station, a setup where engineers can measure, record, and send us raw data for further processing. Right now, I'm in my IDE, an integrated development environment, which is LabVIEW. Let's start with while loop. You'll find it under structures. Drag it onto the block diagram and immediately add a stop button as a control. While loop, what does it actually do? On the front panel, you can always find the description if you go to help and then show context help. Hover over while loop and it says it repeats the code within its subdiagram until a specific condition occurs. A while loop always executes at least one time. In other words, we use while loop because this program will be running on engineers' computers. It will eventually be compiled into an executable file which they can launch directly. And by the way, we'll cover how to compile into an executable in upcoming episodes. If you're interested, let me know in the comments. Our program needs to run continuously and everything inside the while loop will execute at a speed we determine. Basically, the while loop is our heartbeat. It keeps the program alive and ticking at the pace we choose. And no, unfortunately, we cannot set it to run at Silicon Valley speed. That's still undefined. In this example, speed isn't critical, so let's go to timing, add wait in milliseconds, and set a constant delay of 100 milliseconds. Now let's answer the question, where will we get the data from this program? Of course, in real life, engineers supply data, but in this case, we'll use random natural numbers for current and voltage, and resistance will be derivative. We'll calculate it using Ohm's law. As my physics teacher used to say, if you don't know the law of Ohm, stay home. In the Valley, we probably add and don't try to pitch it to your startup to VCs. In structure, select for loop and place it on the block diagram. We can also check its description in context help. It executes its subdiagram n times, where n is the value wired to the count n terminal. The iteration terminal provides the current loop iteration count, which ranges from 0 to n1. For loop here will let us gather random numbers into arrays. The size of the array will match the number of iterations. Output the iteration terminal, which is the count of our iterations up here, and to n or number of iterations add a control and name it records. That records control become our dial. We can turn it up or down, decide how many data points we want. This way we can control the number of iterations. Next, in numeric, select random number from 0 to 1, copy it, duplicate it, and this number will be for current. To get voltage, multiply the random number by 2. Next, we need the bundle function. You'll find it under cluster functions, and we need it 3 times for current, voltage, and resistance. Connect the iteration terminal right away. With this function, we'll combine the individual elements. Next, on the front panel, select an array from NXG Style. You can use any style, I just prefer this one. Choose data containers, array numeric, copy it 3 times, and name them according to the data we want to obtain. That will be current in milliamps, voltage in volts, and resistance in ohms. On the UI side, we are wiring up 3 live feeds, current, voltage, and resistance arrays. We can align them right away by top edges and modify them as we like, by width and by length. So, now you can see them also on the block diagram. Change them all to indicators. Then connect current to our random number. We'll calculate resistance by dividing voltage by current. We connect voltage to the random number that we multiplied by 2, and current goes into the first bundle, voltage into the second, and connect resistance. We need to divide, as I already said, voltage by current by using the division operator. Now we can connect resistance to the corresponding bundle. Next, from array functions, let's add a function build array. Here in context help, it is also convenient to see what connects to what and what this function does. It concatenates multiple arrays or appends elements to an n-dimensional array. We will need to connect voltage and current to this function, so we need to increase it to 2D. So we collect them like this. And now let's add visualization with XY graph. On the front panel, go to NXG Style, Graph, XY Graph, and copy it. On the first graph, we will have current and voltage, and on the second graph, resistance. Current in milliamps, voltage in volts, and also let's name plot 0 and plot 1. And let's name the second graph resistance in ohm. In Silicon Valley, if you don't have a graph in your pitch deck, investors assume your startup doesn't exist. And also, let's give the same name to the plot, resistance in ohms. And let's also change the color on the second graph for clarity and better visualization, for example, to green. Let's find our graphs on the block diagram and connect them. And here we have our current voltage graph. We are connecting to the build array function and also connecting our second graph resistance here. Now let's create and add a global variable. What is it and how do we use it? Let's see. Look for it in the menu, global variable. Place it onto our block diagram, double click, and we get into a hidden subdiagram. What we need to do here is copy the arrays from the front panel and place them in the global variable and also add Boolean. I'll pick I'll pick a vertical one and name it on. Make sure the mechanical action is set correctly. First, let's review the mechanical actions. This Boolean button can have switch when pressed, switch when released, switch until released, latch when pressed, latch when released, and latch until released. For our case, we need latch when released. And if you're curious what these modes mean, we can go through them in future episodes. Let me know in the comments if that's something you want to see. So we save it, name it as we like, and save it in our project in the folder where the project is and file is already created. Call it global1, okay? Saved, close it. Now we need to duplicate it because we have 4 variables. They will be on, current, resistance, and voltage. Move on global variable on a bit to the side for later. Connect current to the number, resistance to resistance, and voltage to voltage. Save and close, and then wrap all of this into a case structure. Go back into structures, choose case structure, and enclose everything. In context help, it says it contains one or more sub-diagrams or cases, exactly one of which executes when the structure executes. The value wired to the case selector determines which case to execute. Everything we programmed now is inside true. There is also false case, but we don't need it now, so leave it as is. And one important point here, let me adjust this part, we don't need so much space here, but yes, make sure the stop button and wait time are outside the case structure. That's critical. Now, let's create buttons for measuring and sending data. This is where numbers will come in. This is where they will be visualized on the graphs. Let's adjust, modify the records and stop buttons, and add 2 more buttons. In Boolean, select text button, we'll need 2. One will measure, take measurement, and we will call the button measure. The second will send data, send to database provider, and it will be called send. It will be labeled send. Now let's quickly work on the button design. First, replace the records control with NXG style since we're keeping everything consistent. This one is numeric control, and the stop button too. Replace it with NXG style Boolean stop. I'd also like to make the stop button bold, and on all the buttons we will remove the label, we don't need it. We'll go to visible items, label, visible items, no label. Let's adjust the size. In properties, set height 40 and width 110. Looks good. That works. Move them a bit here. Now, let's find these buttons on the block diagram. Here's take measurement, and this button will trigger our case structure. So connect it to the case structure, and the on button, global variable on, will be used for sending data. Connect send to database provider. We'll build the database provider in the next episode, and then the 2 programs will communicate and interact. In this program, engineers will measure and send data, and in the next program, we'll receive the raw data and work with it. And that's it for the block diagram. What remains is to arrange the front panel, give it some look, improve the graphical user interface so it's more comfortable and nice to use. Of course, design is a matter of taste, preference. I'll be talking more about design later in upcoming episodes, but for now I'll turn off context help At this stage, it's mostly UI polish, styling the panel so it feels more like a real tool than just a demo. For this episode, we'll leave the program like this. And I want to add a frame here, frame recessed, place it around the entire panel, shrink the unused space so the program will open exactly in the saved view. At the top, I'll add text. Let's call it test station 1 because we'll be building many such test stations, so I'll call this one number 1 as part of a larger program. Ctrl plus will increase text size. Let's increase it to 100 and place it here. Next, go to View, Tools Palette, add background color and color to the text. For example, make it white. Application font, color white, and save. For a more realistic look of the program, let's check how the test station will appear once compiled. Let's go to File, VI Properties, select Category, Window Appearance, uncheck Same as VI, not the same as VI name. Remove the .vi extension, click Custom, Customize, and here we will keep window has title bar. We don't need menu, so run continuously not needed. Allow user to resize no default runtime, so we leave only title bar, run button, and allow the user to close and minimize the window. That way, when compiled, it looks like a real application window, not just a LabVIEW project. Click OK, save, and now run. This is how it looks. Here we adjust the number of records we want. Click measure, and then we send the data we want to share to the database provider program, which we will build in the next episode. For now, I press the stop button, and I want to thank you for joining LaPlante Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to our channel to see upcoming episodes. Thanks for watching!